Hey guys, welcome back to my YouTube channel. You are watching Build AI with Sandeep. We are continuing our Transformer series and we have been learning Transformer architecture for many days. So I will take two more videos to complete this architecture and let's quickly recap our last video that we were in decoder block and our decoder now understand how to look at the past tokens but not the future ones because of masking, because of mask self attention that we have learned in our last video. But that is not enough to generate next word. We also have to give encoder information to the decoder, and that is where cross attention comes into picture. So in today's video, I will explain the cross attention concept step by step. So let's quickly start our today's video. So what is cross attention? So let me tell you that cross attention computes attention between two different sequences by generating queries from one sequence and keys and values from the other sequence. But in normal self attention, what we have done is we are generating query key value matrix from same sequence. There is no other sequence, but in cross attention, query comes from the decoder hidden state and keys and values from the encoder output. Okay, that's clear. So now let me tell you where is the cross attention in this architecture. So cross attention is present at this place. Now you can see there is a difference in cross attention and other attentions, mask attention and normal self attention, that the arrow is coming from this line and three arrows goes into the normal self attention box, and also in case of mask self attention there is a single line. Yes. But in cross attention, there are two lines coming from the encoder output and one line coming from the decoder hidden state. Okay, so let's understand what is happening, what are these arrows representing, and what is happening inside the cross attention block. So let's move to the next slide. And in this slide, we end our last video at this part, at this step. Our masked multi-head self-attention gives us four vectors that represent each token of decoder. Now, what are our tokens? Start, cat, drink, milk. Okay, so we pass embeddings of these words into the masked self-attention block, and then it will returns us four vectors of size 3. Okay, now there is another layer, that is add and norm layer. In this layer we add the original embedding to the output of masked multi-head self-attention. Why we are adding? Because this helps in gradient flow and it preserves the original information that I already explained in my last videos. If you have not watched, please do watch those videos first to understand clearly. Okay, so first we do the add operation, then we apply the normalization. How do we apply normalization? We normalize our vectors using layer normalization, and this will return us vectors, normalized vectors. Okay, so these vectors, these four vectors are the input of our cross attention that are representing each word start, drink, milk. Okay, now as I said that in cross attention query is generating from the decoder hidden state, and that is the decoder hidden state that I referring to, and we will multiply this weight matrix that have learnable values. These values will adjust during the training, and we multiply this weight matrix to our input of cross attention to get the query matrix. Okay, so let's stack up all the vectors vertically, and this will become our denom, that is decoder normalized value, and we will multiply our weight matrix to this denom. Then we will get our query matrix. So yes, so this is our query matrix. Now we need two more matrix, that is key matrix and value matrix, to compute the attention. And yes, so now I did not do the computation for key matrix and value matrix, since I did it multiple times in my last videos. But uh, to give you some comfort, that how do we calculating key and value matrix in our decoder, in our encoder videos, our encoder our encoder this is our encoder block, and this returned us three vectors that represent, and we pass cat, drink, milk. Okay, so we gave our encoder these three words, and these three words uh, becomes the three vectors of size 3 similarly. Okay, so similarly, after stacking up all the three vectors like this will become our 3 into 3 matrix, and we will multiply it to the WK. WK is also 3 into 3 matrix, and this will give us the key matrix that we can see over here. This is our key matrix. Similarly, we compute our value matrix. Now we all know what will happen after this. We saw the how do we compute attention. We use this formula. We use this formula, that is softmax of query key transpose. We scale, we divide by dimension. This is dimension k. In our case, what is our dimension? It is 3. Okay, so we do scaling using dimension 3, and after that we multiply with the value matrix. Okay, so first we calculate this part, query key transpose. So our now I already told you that what is query. Query is basically what we want to search. Okay, and in this query, each row is representing each word of the decoder, each token of the decoder. So first row representing start, second cat, third drink, and fourth is milk. Okay, so each row is representing each decoder token. Similarly, key also each row representing each word, and cat, drink, milk. Similarly for the value matrix. Okay, now our query matrix is of size 4 into 3, and our key matrix is of size 3 into 3. When we do multiply both the matrix, then we will get our score matrix, and score matrix is of size 4 into 3, because 3 cancel out and we will get 4 into 3 matrix, and this is our row score matrix. Okay, and again each row is representing each decoder token 1 2 3 4. Okay, now the values in the row score matrix are random. These are not probabilities. So to convert these values into the probability, we apply the softmax function, and we already know what is the softmax formula. Softmax formula is I equal 1 to n e I. Okay, Okay, so basically, to compute the softmax of the first row. Okay, so what you do is E2 divided by E2 plus E1 plus E.5. Okay, this will give us the value, the first value here. Similarly, in second place, what we do is we will do 1. We will change 2 to 1 and everything is same. So in that way, this way we can calculate our softmax values, and these are the probabilities. So yes, now softmax is applied row by row because each decoder token distributes attention over encoder tokens. So this is our row score matrix. Softmax is applied row by row, and each decoder token distributes attention over encoder token. Now final attention weight matrix we will get, and these are our probabilities for start word. And now what it is saying that that let's understand this way, that next step is our attention weight matrix multiply with value matrix. Okay, and it will give us 4 into 3 matrix. 3 will cancel down, and our value matrix is this, and each row is representing each encoder input word. And what are the words, what was the sentence? Cat drink milk. So now the start word gives 63% importance to the cat word, 23% importance to the drink word, and 14% importance to the milk word. Similarly, cat word gives 61% importance to the cat word, 19% importance to the drink word, and 20% importance to the milk word. So this is what this whole mechanism is saying. Now we will multiply this attention weight matrix to the value matrix, and we will get our final cross attention output that represent each row represent again each decoder token. Okay, so uh, what this line says, multiplying the attention weights with the value vectors produces one context aware output vector per decoder token. Okay, so these vectors are context aware that have the information of the encoder output, and this is what we wanted to achieve. Cross attention is basically the bridge between the encoder and decoder, and it helps to get the encoder output, encoder information, what encoder gives us in output, and how do we use? We use with the help of cross attention. Okay, and now you saw that in encoder we have 4 tokens, and in decoder we have 4 tokens, but in encoder we have 3 tokens. Okay, so that does not create any kind of problems because of self attention. Okay, vector size stays the same. You can see that each vector is of size 3. Okay, encoder length only affect, yeah, so encoder length only affect attention distribution, not output size. Okay, so yes, so this is the today's topic, and that is all about cross attention. And after getting after cross attention completes, these vectors goes again into the add and home layer. After that there is a feed forward network. So these two already done by me in my last videos. Okay, done. And in next two videos I will explain these two concepts, and then our transformer architecture will be complete. So yeah, that is all about cross attention. And if this video helps, then please like and subscribe to the channel. and thank you for watching. I will see you in my next video.